all the same. You just have to understand how do you transfer them from the language of the medical guys to the language of, for example, the industry. So feel free to adapt them in your areas of expertise. Good. So, if you remember vividly, the breast cancer data set, we said it is gotten from, I think, Wisconsin University, and it is in the scikit-learn Python package. And we said the goal of this data set is to classify tumors as malignant or cancerous or benign, which is non-cancerous, based on various features that were derived from digitalized images of breast tissue. Now, the size of this data set is not that big. It's just 569, which is also fine for machine learning. Another emphasis I want to make in the course of this class is that machine learning is data hungry. So the more the data, the more better the performance of the model. Remember, the machine is learning, so it relies on the data set you give it. So if you could get much data set, the model will be happy, because in that case, you will understand if the model is overfitting, underfitting, or it's actually picking up signals. So there are 30 numerical features that include measurement like radius, texture, parameter, area, smoothness, compactness, and so on. And then the dimension of the class or the target variable it's just a binary classification problem. And I could see how far we could go today, but hopefully we are going to be able to do a multi-class problem as well. So the first thing we are going to do, of course, we will train the data. We'll look at the data set from two angles. The post-hoc explanation from two angles. We'll look at SHAP, and then we looked at LIME, and then we could see how far we go. So like I always tell you, the first thing you should do is to load the relevant packages that you want. But sometimes along the line, you discover, oh, this package is missing. Feel free to always include it. So once you load that, you load the data set. Like I said, this data set, it's an scikit-learn data set. So you could always import it from the package. And then also the target variable is there. So, however, when we would like this data set to be in data frame format, so that's what you see we're doing here. So, like I tell you always, try to have an interaction with your data set so you could be able to know the data very well. So don't get tired of performing EDA. Most of the time, that gives you a lot of insight into what your data is all about. So that's what we are doing here. You see, we perform the EDA. So what did we just do? We just try to view the brief of the data to see how this instances looks like, and also to have information on the nature of the data type. Is it a float? Is it a string? Is it an integer, and so on. So you could also see from here, we quickly know that this data set do not have a missing value or missing observation, because we could see all of them are 569. So it means it's complete and it's fine. So the next thing we do, we check some descriptive statistics using the df.describe. So this gives us a brief about the mean, the standard deviation, the minimal, the 25th, 50, 75, I think percentiles, and also the maximum in the data set. So having, you could also, through this approach, you could know if the data set is going to be skewed or it's going to be normally distributed. Now, the next thing you could always do, try to check for missing values, because if you don't check for missing observation, you are likely going to have issues during modeling. But some of the algorithm, of course, they can detect missing values, and they could do, like the decision tree models handle missing values fine. But it's good to have to tackle missing observation if you have them. And of course, if you want to tackle it, remember I taught you guys you can use the mean median mode, or and any other approaches like imputational approaches. You can even use neighborhood approaches or random forest imputation. You could also try to drop them if it's an issue. But in the situation where maybe you have a large sample, most times when the missing value is less than, I think 10%, you could drop them. But again, that means you are going to lose some information. So weigh the options very well before you think of what to do with missing value. So the next thing we're going to do is to visualize the data set to see how this data set is distributed. And good visualization, like histogram, whenever you're dealing with continuous variable. When you are dealing with binary variable, you could talk of bar chart. I think in the first part of this class, we talk about what a good visualization means, or how you could select visuals. So now, the next thing, yeah, this could take some time because the variables are much, but now it makes sense if we could have an overview of how the data set looks like. So you could see there are some normally distributed, like I think this mean or smoothness seems to be normally distributed, but some are tilted to the left, and I don't see anyone really tilted to the right. I think most of them are tilted to the left. But we could quickly see that the target is not is not a continuous variable. We could actually see that there is 0 here and there is 1 here, which shows it's a binary or categorical variable. Now, the next thing we're going to do is to check using box plot. Now, box plot is a good plot that you could see if there is a presence of an outlier. And you remember, an outlier is something that is out of the 75 and 25 quantiles or percentiles. Once it is out of them, of those range, he said it's but again, outliers, it depends on what kind of task you are looking at. If your work is not really focusing on these areas, you can continue with your analysis. But if it's something sensitive and you think the outliers are going to mess up with your predictions, then you could see how you could trim it by removing those outliers. Now, the moment we perform that, it's going to give us good. So now we could see. However, I want to make an emphasis on this. If you notice, I added this points here to increase the font size of the graph, because if you don't do that, you will notice that by the time you do your visuals and you're putting them in a manuscript, most of the time I do review some papers. Sometimes you see the authors sending you the plot. One in you discover that the graphics pixels are very poor. So that being said, by the time that paper even scales through to be published, after some years, when you come back to read those papers, you see the images become blurred. Then another thing again that I used to identify is that the font sizes are small sometimes. So because of that, it makes a lot of people to try to strain their eyes to understand what is really happening, and that's not good. You wouldn't want people to, because some people have to, right, you use an aid of a glass, to see. So you have to put all of these things into consideration, and if you are doing these things for your audience, not for your own consumption, you have to make sure you fit it in a way that it makes sense. So feel free to play around with the font size. You can increase it to 18, to 20. In fact, there are some plots that we rate this up to maybe 30. If we have to make sure we stream those plots to be very small on the manuscript, we make sure the font size is readable. So make sure anything you're doing, the font size is readable. Take note of that. Okay, so you don't forget. So the next thing we are going to do, of course, we are going to check for issues around, remember, multi-collinearity. So again, like I used to say, if the task is not important, then you could forget about it, but it helps you to be able to see which features are messing up with each other and have the potential of affecting your prediction. So that's why it's good for you to perform the correlation heat map plot, so you could have an overview of what's happening. Good. Now, when we do that, you could actually see that these two features here are actually highly correlated. You could see the mean parameter and the mean area. These two features are seems to be competing with each other. So if you think of what you would do to that kind of features. Generally, we see the features around this thing seems to be highly correlated with each other. Another thing we could spot you could see some here, and also we could see yeah, still here. You could see there are some, things happening here. We could also see some here. So, I know that. So, again, like I said, if the task is what requires, then you think of removing them. However, in this case, I won't be surprised because these are mean of a particular thing that is highly related. So I would expect this kind of correlation to spring up. And the aim of this task is not really to read out some of these things. So we will leave the futures along the line and see what later happens. So let's be patient with ourselves on that. So the next thing is to now we want to go into the modeling side of the work. So the modeling phase of the work, I think I'm supposed to have said modeling. So in the modeling phase, we would likely have to start by dropping the target variable from the data set so we identify what is the features and what is the target or dependent variable, which is what we have done here. And then remember, like I said, before you jump into the modeling, you will always have to just keep some aside. So it's like, you don't want to use up everything for the model training. You have to keep some that you say, this one is withhold. I want to use it to validate the performance of the model. So that's what we are going to do here by splitting the data set into 80% training and 20% testing. So this 0.2 here represents the testing size. So once we run that, which we have done, the next thing is for us to perform, we want to normalize or scale the data set because although for decision tree models, it's not a problem, but it's a good practice because sometimes you never know when these features could be nuisance in their behavior. So it's good you always keep it in the loop. But for decision trees, it's fine. You don't really need to scale. But like I said, it's a good practice if you scale. So first, what we are using the standard Scala, and also there are other approaches like robust Scala and so on and so forth. You could use any of them, but I think the standard Scala seems to be the most very popular one, and I think one of the reasons is because it's sort of robust to our layers, but it do have its own limitations. So you could try other approaches of scaling. So quickly, when you run that, you fit the scale on the training set, but you transform it on the testing set. And the moment the training and testing are having different feature size, it will raise an error. So we are going to train first random forest for this task, but I jumped the step, which is I was supposed to first fit the random forest without grid search. But now I'm putting everything together with the grid search because of course we have shown you guys in previous classes so how you could be able to train it first without grid search and then with grid search. But here I just put everything together because I feel you have matured to that level to understand that's not an issue jumping that step. So that's what we do. So I'm going to perform a grid search, and then this CV here is cross validation and splitting it into 5 fold. That's it means in each fold there is a train and test, train and test, train and test. Then at the end of the day, it averages and give us the strat. Right now, the CV, if the data set is very large, it will take time but most times if it's not large, it could quickly run. Another thing for you to take note of is the scoring. This scoring here, you could play around with it, especially if your data set is highly imbalanced, you could play around with it. But in the case of this particular instance, I don't think we have case with imbalance, but let me see if we do have case with imbalance. So I'm going to check for the target variable to see if there is anything around imbalance. Let me just copy this. So now we could say dot value. I think counts. No value. Value counts. Let me see. Good. So when you check, you can see it doesn't have much differences. We have 357 against 212. So there is slightly imbalance. So it's fine. It's not an issue. So we wouldn't have to expect that it will figure because they seems to be quite close to each other. But when it's very, very small, that's when you'll be scared that the imbalance could mess it up. So the random state is 42, and then the cross-validation splitting strategy, then the scoring is accuracy. So we're going to train now the model to see, and then we also evaluate after training, we evaluate on the testing, this testing here that we set aside. So that's what we are going to do. So by the time the random forest finish running, remember, because of the grid start, it will take time because it will have to do for 100 estimators, 200. In fact, there are situations where we could have lots of these estimators to go around them. So, but now the random forest return best parameters. These ones help us to identify the best estimators in that we discovered for this task. Now, in fact, the maximum depth is none, the minimum sample is 2, and the estimators is 200. So it means that it go for this instead of this. And then let's look at the scoring. We could see for the precision, we had almost everything, it got almost everything right. We have 98, 93, 95, and this is 96, 99, 97. And the accuracy, it tells us it's 96, and the macro average is around 97, 96, and the micro, I think, weighted average is also around 96. So the classifier is super good. It's really excellent for this start. So another thing again is that this is not just enough. Remember, we need to have a global explanation of which feature is pushing this prediction. Which feature is telling us that this one is supposed to be this one is supposed to be this? We need to understand which feature is contributing to this prediction. So the feature importance help us to unravel this mystery for us to be able to understand which feature is pushing them. So that's what you see we are doing here. So by the time you run this, you'll see that. And again, remember, like I always used to say, I did increase the font size so that you can be able to have, when you are going to put it, for example, if you want to get a manuscript, you have a very good visuals. So that's why we did that, this. Now, we only display the top 10. You see, we only went for the top 10 futures. So in this top 10 futures, we can see the worst area and the worst concave point and the worst parameters are like the topmost. We have the mean concave point also, the worst radius, and a bit of the mean parameters. So that's a good one, but it's not just enough because this is a global explanation that the entirety of the model, these are the most resilient top 10 features that are pushing the prediction. So we will also like to have a plot of the AUROC to see what areas we are leaving out to chance and which areas we actually get correctly. So the AUROC is very good. We have around 100, but of course, I'm not agreeing with this because this is super, super good. Like, if I have an AUC more than 96, 97, I really question if what we are having is not uh overfitted. But again, this is a very well-known example, so I wouldn't be surprised because, of course, it's even an sklearn data set, so I should expect this. But in real life examples, you may not have up to this. You have to struggle to tweak, to change, to manipulate before you get this great example. So, but it's a good one. It is not a bad one. All right. So, the next thing is, this is not just enough because I noticed we have been looking at only random forest. I wanted you guys to also see or have a feel of other interesting algorithms out there. The XGBoost belongs to the boosting algorithm families that uses the approach that we call bagging and assemble. So it uses I think I did work with those things during my master when I was trying to find a way I could be able to overcome the issues that came with support vector machine. So that was when I came across the boosting algorithms, and the XGBoost belongs to that family. There are other families that you could also come across that are very, very interesting, but the XGBoost seems to be very popular. And for some time now, XGBoost have been really, really doing very great, even much greater than, in some cases, the complex neural network models, especially when it comes to tabular data set. You really have to give your your onions to XGBoost. It really solved the problems very well. So most of the competition, for example, in cargo, you see that XGBoost always emerges as the winning model. So that's why a lot of people really like it. Many data scientists use it. A lot of practitioners usually explore it. So alongside that, random forest is very popular. XGBoost is another very interesting model for you to fit. And if we have to go into the whole Dogon of this XGBoost, we have to look at the D matrix and all that and all that. And like I said, I don't like, I'm trying to hide some of the mathematics and just explain it to you so you could be able to understand it like you're fine. So that's why sometimes I try to keep the math out of it. But notwithstanding, you can look out to the maths of these things, how the boosting, stacking, and also the bagging works and the assembling of some of these trees, and how the gradients and all that works. Could always look at it to understand these approaches very well. But the SGBoost, again, just like we did in random forest, we remember it's a boosting family, so it's still in the decision three family of algorithms like the random forest, but it's kind of more higher than the random forest to say. So we could say in the rank area of complexity, the XGBoost, of course, is complex than random forest. So we have the estimators, the maximum depth, the learning rate. So again, because we build like sort of matrix, so that matrix create like a partition inside the whole thing. So that's why we have to have a learning rate because it will be releasing them in batches. Like I said, again, I really want to bother you guys much about this thing. So what we do again, like we did in random forest, we perform the grid search, we fit it using the best parameters from the grid search, and then we make predictions to see the best model. Then again, sometimes the XGBoost may take much time than your random forest. Sometimes you could train faster, but usually as the complexity increases, the computational time increases, the MP problem, remember. So take note of some of these things. But I think in our case, the data instance are quite few, so I don't expect it to take time, of course. So again, you can see the best parameters for XGBoost. We have a learning rate of 0.1. Let's look at the learning rate. We have 0.05 to 0.1. Again, it went for the extreme part of it. So the maximum depth is around 3, and also the estimator, it went for 200. So it all went for this one except for the maximum depth. Now let's look at the performance classification report. Now in the repo, we have a precision with 95, while random forest did say that the precision was 98 for the cancerous classes, while the non-cancerous was 96. Recall dropped to 93 and 97. F1 score dropped to 94 and 97. And then the accuracy is 96. The same with random forest, 96. So if you ask me, I would opt for XGBoost because I could actually be more comfortable with XGBoost than with random forest, despite that random forest is doing well. And I will tell you one of my reasons is because the random forest went for maximum depth, none. I think I would be uncomfortable and suspect some sort of overfitting here. But rather in the XGBoost, we are able to have a maximum tree of around of 3, which makes sense to me. And again, I could see there were some drops here. Like I always say, we don't expect a perfect model, but at least a model that does very well. So I would be much more comfortable with the with the XGBoost, despite that the random forest performed very well. So again, let's look at the future importance, see what's happening. Now, looking at the future importance, the mean concave point emerges as the most important feature here, while in random forest, it was the mean concave point. It was 1, 2, 3, 4. It was the 4th feature in random forest. But in XGBoost, it's actually the 1st feature. Then the worst concave point, which was the 1st in random forest, like we see here, it was the 2nd in random forest. It's actually the I think it's the 2nd. And then the worst radius, let's see, the worst area is the 1st in random forest, but the worst area is 1, 2, 3, 4, 5, 6. So it's the 6th here. So you can now begin to understand what we are saying. These models have a way of viewing what is most important. Now you see why we always want to have some sort of a consensus. Because if you use random forest, you use XGBoost, now you're having different features popping up as the most important. So just fact that we do not have one constant feature that you'll be saying, this is the champion here. It gives room for you to explore other approaches. If we settled down for only random forest, we could have said, oh, the features random forest gave us are the most important. And you'll see somebody will be standing and defending it and saying, this is the best. So, but when you explore other approaches, it makes you now to have a more broader view of it rather than from one perspective. So again, let's look at the AUROC curve for XGBoost to see how the performance will look like. Now, it dropped to 99 instead of 100 that we saw in random forest. So again, it's fine, although it's still high for me, but I think it's not bad. We could go with that. So now, having looked at all this, we can, if we stop here and say this model deploys it, it's fine, it could work. But again, the problem is, will the clinicians trust what you have done? Because the clinicians do not know how you arrive at these beautiful performances that you have shown. So the clinicians would like to explore, to understand, so they could be able to trust the decisions that you're getting from this model. So that's what brings about the post-hoc model interpretation of the model that we have. Okay, so sorry, Darian, can you mute?
Oh, okay.
Thank you. So that's what gives us the post-hoc explanation of this model. So the next thing we are going to do is to now do the SHAP. So remember, like we said, for you to do the SHAP, you need to get it into that wrap it around the output or the model that you already have. So that's what we do here. So we have the SHAP 3 explainer. Remember the H3 explainer, because the XGBoost, like I told you earlier, it still belongs to the decision tree family. So we are wrapping it around the SHAP first. Then at the end of the day, when we do that, we will now make predictions on it. That's what we do. So yeah, interesting. This thing wastes time. So the next thing we are going to do is to visualize to see what is pushing which thing forward and which is pushing which thing backward. Now you can see interestingly, SHAP does not think that the global explanation. Now, okay, so the mean concave point is the most important thing. So good, the mean concave point is here. Now, the thing is, when we look at the SHAP, you can see that some of it, the high value of the low instances actually pushes the prediction forward, but this small value pushes the high value in the negative direction, pushes it towards this other direction. So again, the dots plot did make sense. We could see how each of those features contributes to the predictions in the model. However, let's try to look at another kind of SHAP explanation plot called the waterfall plot. And again, if you want detail of the SHAP explanation, you have to refer back to our previous class to see how we have talked on that. Like, I didn't want us to waste much time on SHAP today, so we could look at the line. But one thing we could see is that there are lots of the mean concave for this instance. For example, we picked the first 3 sample instances in our data set. So for the first patient, or yes, yeah, permit me to use the word patients for this case. So let's say the first patient, you can see that the positive values of this mean concave, worst concave, worst areas, all these values in red are actually pushing the predictions forward. And at the end of the day, we could actually say this person is cancerous, or and all that. Then when you look at this other person, on the other hand, you will see that the situation is not the same for the second patient. The second patient, all these values are in the negative or direction, or the blue direction. It's just this worst symmetry that we see that is positive here. So this patient status and this patient status are not going to be the same. For example, you could also see when you look at the density, you can see this one was 4.985, and this person here, the density is around minus 7.237. And then when you look at the expectation, it's around 0.54, even though I think this expectation seems to show the same. But no, I wouldn't rely on the expectation. Let's look at this density. You can see that the density are not the same. This is actually tilted towards the positive direction, while this one is tilted towards the negative direction. Now, when we also look at the third patient, you could also see that the third patient is not the same with this person. You can see there are differences, but also this one has a density of around minus 6.689. So again, this is tilted towards the non-cancerous. Okay, so we can say that person is non-cancerous. So the next thing we want to do is to look at the values in the column. Then now we want to jump into the line explanation. Now, the reason is because, again, the line, we want to see how line is explaining a particular instance. Remember, this one is an instance in the data set. So this person is, we are just looking at the first three instances, you know. Now, we want to look at the same problem, but we are looking at it from a different angle using the line explanation. So let's see what line explanation is going to give us. So first of all, remember to install using the pep .install the line before you could be able to import it. So do that when you're running the script. So again, we create a line explainer. So just like we wrapped it around SHAP, remember, we do the same by creating a line explainer. But remember, the line, we have to build what? A simple model. Remember, in this case, you're building a simple model. Do not forget, we're building what? A simple model to explain the prediction for us. So it's a surrogate. So that's why you see that when we are creating, we put the training, we put the label of the training, the mode, we put the features, we put the class name, discretize, and all that, because we are building a surrogate model. So it's just like I tell people that word, before God formed or creates the earth, he has to first of all call out light. Then he started building the earth on top. So the complexity started and then started bringing out from it. And I think I did had a Medium article I wrote about the 6-day creation or something. But you could explore that on Medium to see how that creation, tell us about establishing businesses and all that. So it's the same way you build from that complex to simpler approaches. So you have to first build the line model on a simple classifiers like linear regression, decision tree, and so on and so forth. By the time you do that, then you can be able to work. You can be able to now perturb the original model you have. Do you understand? So you build that simple model, then you can perturb it around that complex model, because it will now pick a part from that complex model and then see what's happening. So let's pick our first one instance, and then we check how the prediction of that particular instance is going to look at. And then we are looking at the 10 most important features. Of course, we don't have to do everything, so we're just looking at the 10 features. So we have done that. So now let's make the visuals to see what happened. Good. So these are run. So the good thing about SHAP is very, very friendly. It helps us to see what is happening, what's not happening. Very easy for us to interpret. So let's see. This person, SHAP, was actually very sure that this person is 99.9% malignant, cancerous. Now, if that person is cancerous, let's see what's happening. You can see the topmost feature, the worst, is actually on the negative side. However, you could see these features: worst texture, worst area, worst radius, mean texture, worst concave, worst parameter, mean area. They are all red. They are all pushing the prediction in this direction. Now let's look at also the future value summary. You could see this value is only just few values here: the symmetry, error, and the worst concave that are blue. The other values are all showing they are contributing to making these patients to be malignant. Is this not beautiful and interesting? Because you can now see why someone can be classified as malignant, and why the other person is classified as benign. So another thing, again, you can see from the local explanation, again, the worst concavity is, like I said, is on the negative side. But you see, all the other features, they are on the positive side. They're on the positive side. They are pushing it towards this direction. So the green color here is actually the ones that are pushing it into this direction. So I don't know if you guys are with me. Are you guys with me?
Yes, doctor.
Yeah.
Hear me?
Yes, doctor. Yes.
Yes.
Oh, great.
Yeah, we can hear you.
So I don't want to be talking to myself alone. So I have to make it.
No,
I
you're
have
not
to.
talking to yourself.
All right. Okay, so another thing we want to do now, we want to look at multiple instances. Remember, this is we looked at the first instance, that's instance NDA here is 0. So let's look at the first I think we're looking at the first 3 instances. So yeah, 5. Let's look at the first 5 instances here. So we will run this for the first 5 instances to see how these 5 people will look like. So again, the first person, remember we said is around 99. But remember, like we said, this perturbation that we are doing, each time we come back, it's always going to be, like I said, it's not this fixed, okay? So each run, it changes. You could see here, it's kind of fine, but for this person, it changes. The worst concavity is still there. The worst symmetry is still blue. Then worst mean concave point is blue. But it's 99% sure that this person is cancerous. Now, when you go to the second patient, you can see the second patient is benign. And it's 100% sure that the second patient is benign. And why is it 100? You could see all the values are on the negative, all pushing towards, they are all blue except for one, the worst symmetry. The worst symmetry here. But you see, in the case of people that are cancerous, the worst symmetry is blue. But for the people that are benign, the worst symmetry is orange. So it's actually telling us something, we're building something. Now, the next patient here is also 100% sure that this person is benign, or this patient is benign. Again, we have the worst concave points to be orange. Now, if you go back here, you see the worst concave. I think, let me see if it's here. The worst concave, the worst concave here for benign was orange. But for this person, this person is still considered non-cancerous, but their worst concave point is orange. Now, this person here is 100% sure that this person is cancerous. And again, you could see it's only the worst concave is blue. All the other features are yellow, orange. So this is quite interesting. You see that this person, all of them are on. So when a clinician looks at this, he quickly have understanding that, oh, this is it. You don't even need to do much of the talking, because this on its own create visuals that every layman could easily understand. The same thing when you go to another patient that is benign, this person is cancerous. The same thing for this person, all of them, all the values are orange. All the values for this patient are orange. So interesting, beautiful. So now you could see that with this, you can be able to explain. But now remember the limitations that we highlighted earlier on. As good as this could be, we could still put into consideration the issues around the dependency, lack of interaction, and so on and so forth. So when you are giving the explanation, do not come and say, I'm 100% sure. No, you have to make sure you highlight some of these limitations to your audience and say, but from what you discovered, it's actually pointing towards this direction. So the clinicians could actually use this like a guidebook in order for them to make much more robust decisions that are much more effective.